Okay, so for the rest of this lecture, I'm just going to go back to give you a bit of a simplified history of artificial intelligence from the 1940s up and through the 1950s. Most work was focused on studying the brain and trying to have models that are based on the brain. Then there was a period where symbolic reasoning and expert systems dominated the field. Then there was the rise of neural networks and genetic algorithms and things like fuzzy logic, things that we refer to as adaptive behavior, behavior-based robotics. And then we'll have a look at just a few of the topics that are of current interest. So these brain-based models, McCulloch and Pitts came up with a mathematical model of a neuron. They looked at individual neurons in the brain and tried to come up with a mathematical model of the behavior of a neuron based on its inputs from other neurons. Then Norbert Wiener invented this term called cybernetics. Cybernetics comes from the Greek word kubernatos, which means the person who steers a ship by putting his hand on the rudder and steering the ship. So the idea is there's sort of a ghost in the machine, the control mechanism of a robot. This word seems to have fallen mostly into disuse now. There's something sort of cool about it. Alan Turing that we talked about before, as well as having the Turing test and the Turing machine and the code breaking and all the other amazing things he achieved, at the very end of his life, he also did some very early work on neural networks. And these manuscripts were not published until after his death, but he actually is talking about A-type networks and B-type networks, and it's historically very interesting to have a look at those. In the 50s, people like Selfridge were working on pattern recognition. Hubel and Wiesel looked at the vision system, the visual cortex. They figured out that there are certain neurons in the primary visual cortex which respond to lines in a particular direction. There's a whole course on image processing, there's a whole topic in itself, but there was a paradox for many years. When you look at, say, telegraph wires in the distance or telephone wires, the angle subtended by that wire is so thin that it's kind of a mystery how you're even able to see such a wire when you look. And it turns out there's mechanisms in our brain that actually enhance straight lines and bring them out in the image, kind of thing. And these guys figured out how that works. That there are these neurons that only respond to a line at a particular angle. And then I think people later realized there are ones that respond to lines that are moving in a particular direction, that sort of thing. And I think there were these sort of slightly nasty experiments they did on cats, where they bring cats up in an environment where they're not able to tilt their head, and they're only exposed to lines that are vertical, and then later on those cats are they don't develop the ability to see horizontal lines. If you give them something horizontal, they have to tilt their head. They can see it. And Frank Rosenbach developed the perceptron learning algorithm, which was the beginning of neural networks. Now, in parallel to that, people were working on symbolic reasoning. So Alan Newell and Herb Simon were, when they showed up everyone else came to this 1956 conference with just abstract ideas and waffle and blah blah. They actually came with a program that they had written called The Logical Theorist. So they actually had something interesting to show. John McCarthy, who just died recently, I think in 2011, he invented a language called Lisp, which was the favoured language for artificial intelligence research for many years. We talked about the ELIZA program of Weizenbaum, and Feigenbaum wrote a program called Dendrol, which is similar to ELIZA, but it was a very early expert system. It tries to from the symptoms that a patient has, it tries to figure out the best drug or the best treatment to prescribe to that patient. Now in 1969, Marvin Minsky and Seymour Papert published a book called Perceptrons, in which they emphasized the limitation of neural models, and they went down to Washington and lobbied agencies to try to redirect the research funding into symbolic approaches. Now, whether it was because of their efforts or for other reasons is a matter of debate. In any case, from the period from 1969 to 1984, there wasn't much work done on these neural models, and there wasn't much work done on machine learning either. That was the period of expert systems. You know, most of the work done was on expert systems. There were a few exceptions. There were a few researchers who continued to work on these other approaches, but very few. Now, these expert systems saw some commercial success, but they ran into difficulty, partly because of a combinatorial explosion in the search space, and the difficulty of formalizing everyday knowledge as well as expert knowledge. So these expert systems, the way it worked, the idea behind it was you invite an expert in a particular field. So if it's medical diagnosis, you invite a doctor in and you interview that person and ask them how they make a diagnosis, and then you try to code into your program the way they arrive at their decisions. But yeah, it turns out there's a lot of this everyday knowledge eventually catches up with you. You know, so what do I mean by everyday knowledge? Well, if a cup is red and I turn it upside down, then it's still red. Okay. If a cup is full of water and I turn it upside down, it's not still full of water. It sounds silly to say these things, but unless that's programmed in, these expert systems wouldn't be able to figure it out for themselves. You know, and there were these huge attempts like Psych and so on in the 1980s to try to program in as much of that everyday knowledge as possible, but there was always new things that they hadn't thought of before. And so this led to what was sometimes referred to as the AI winter, that funding agencies and industry just got sick of the whole thing, said, oh, this AI thing's never going to work, let's just cut the funding. But then, from 1986 onwards, there was a renewed interest in these neural models and adaptive computing. So there was a special 2-year project at the University of California, San Diego, where they're looking at the parallel distributed processing. There was new techniques developed for brain imaging and neurobiology. There was this field of cognitive science started to spring up and get more important. There was Rodney Brooks with his behavior-based robotics, so less emphasis on the symbolic approach and more emphasis on low-level behaviors. And as I said, this adaptive computing framework. Now, parallel to this, there's the issue of game playing. So I could have included Babbage and Lovelace in this slide. In the 19th century, they had a plan to build a computer to play tic-tac-toe, and they were going to tour it around the country and show it at country fairs and so on, but they never managed to build it. But this paper by Arthur Samuel from 1959 is really a classic in computer science as well as artificial intelligence. It contains a lot of very interesting ideas. He was describing how he was trying to build a checkers player. And another game people looked at was backgammon. So Hans Berliner in 1979 wrote a backgammon playing program. It was able to beat the human champion at 1 or 2 games, but not in a whole match. The humans still had the edge until 1992, when Gerald Tazara's program TD Gammon actually was able to beat the human champions, and it was a very big success for reinforcement learning. This checkers program, again, the humans still had the edge up until 1994, Jonathan Schaefer's program Chinook. And chess, of course, in 1997, Deep Blue managed to defeat Kasparov, and the humans have exited the field ever since. And after chess was done, from 2006 until the present, there's been a lot of work on this Chinese or Japanese game of Go using Monte Carlo tree search. I believe the computers are able to beat the humans on very small boards of 9 by 9. But so far, the humans still have the edge on the standard 19 by 19 board. But it'll be interesting to see where that goes. These are just a few current topics. This isn't a comprehensive view necessarily of what's going on now, but there's been a lot of interest in probabilistic models and statistical models, models based on Bayesian mathematics, models based on sophisticated statistics, for robot navigation and text processing and all kinds of other tasks. So if you're interested in continuing with AI, you might think about taking a math course in probability or statistics. There's been a lot of work in reinforcement learning. There's moves to kind of make integrative and hierarchical approaches and large systems. I mentioned IBM DQA program that won Jeopardy last year. And of course there's a lot of work in robotics as well. Military robots, domestic robots. In this school there's been a lot of work on Rotary Cup soccer and rescue. And some of my colleagues in NICTA have also been involved in this DARPA Grand Challenge for autonomous driving. And one good reference for this material is a book by Nils Nilsson, Quest for Artificial Intelligence, History of Ideas and Achievements. I actually don't have a copy of this book to show you, but you can actually download a soft copy from this website and have a look at it. Okay, well that's quite a lot of material for today. I think we're going to take a 15-minute early mark today, and then on Thursday we'll look at other search techniques.